let's investigate some confidence intervals for two proportion situations. So this would be where we have two distinct populations and we're asking some sort of categorical, so yes, no type of question. So in this particular one, the description, the examples provided in the description, so take a look there. The first thing we want to know is, are the samples large enough? And what do we mean, are they large enough? Well, are they large enough to proceed with our confidence interval process? We know that whenever we're creating confidence intervals or doing hypothesis tests, it's based on the idea that we've satisfied some conditions. So for example, were our samples random, simple random samples? In this case, we'll assume that they were. But the other piece is having a large enough sample. For proportions, usually we're trying to make sure we have at least 10 successes and 10 failures. If we have two populations, that means 10 successes, 10 failures from each. And if we don't have population values, if we don't know the true value of P1 and P2, we're going to use P hat instead. So we want to know, okay, is N1 P1 hat, is that at least 10? Well, this is another way of saying the number of successes from sample one. Since in this problem we were already just told the number of successes was 17, we can say, okay, we don't have to actually calculate N1 and P1 hat. We can just say we have 17 successes. That's at least 10, so we're in good shape there. If we want to know N1 times 1 minus P1 hat, we can say, well, that's just the number of failures. So we can take our sample size, 25, and say, okay, if we had 17 successes, we can subtract that. So I guess we had 8 failures. Now that's not at least 10, so that's a problem. We could keep going, and I will have us keep going just to be thorough. But even at that stage, we kind of already know our sample from our sample one from population one is not quite large enough. Let's check though whether sample two was large enough. In this one, we were told that the number of successes, the number of students who live in off-campus housing, in college-owned housing, was 4. Well, okay, that also is not good enough. So even sample 2 has some problems. The number of failures would be, right, that sample size, so 20 minus the number of successes, 4. So if we get 16, okay, that one actually is fine. That's at least 10, so that's good. So there's a little bit of an issue here with our sample sizes. Now, normally we would say, well, we could proceed, but we'd have to have some caveats. We might have to change our process a little bit. Really, you would want to make sure your samples are large enough. What I'm going to say here is, regardless of what we said in A, which was that no, our sample sizes, our samples were not large enough. Regardless of that, let's proceed and at least go through the process of finding a 99% confidence interval. Because the process is going to be the same. The validity changes based on whether our samples are large enough or not. So there are formulaic ways to go through this. So we could find our test statistic and kind of go through that process. I'm going to show us more so the process using our TI 83 or 84 calculators. So like most of the time, we go stat and then over to tests. And then we got to make sure we're selecting the correct one. So first of all, we want a confidence interval. So it's going to say interval or int in there. And then secondly, we have 2 proportions. So there's 2 sample and 2 prop, right? 2 sample has to do with means, 2 prop has to do with proportions. So we're going to say we want a 2 prop. And with means, we had a choice sometimes between Z and T. Now here we don't have that choice. There's only going to be a 2 prop Z interval. So that's kind of nice. If we know what scenario we're in, we don't even really have to make a choice. Now when we go into that test, it's going to ask us basically about, well, how many successes and what were our sample size for each of these samples. So if we run through that that interval, so 2 prop z int. So it's just going to say, okay, what's x1, what's n1, what's x2, what's n2, right? And thankfully in this problem, we were given those things. That's sort of what we already talked about here. How many successes? Well, we had 17 out of 25 successes, and then 4 successes out of 20. And then the only other thing it asks is, what's your confidence level, your C level? And for us, if we want 99%, we're going to say 0.99. And then after that, we're going to get some result, right? We calculate this, and we end up with an interval 0.14709 to 0.81291. So there are a couple things we can say about this. First of all, right, P1 minus P2, keep your order in mind. If you switch these, this interval is going to flip around and have negative values. So it'll be negative 0.8 to negative 0.1 and change. Right, so the meaning of that can definitely flip around. So in this case, we had Pacific University as our population 1, and we had PSU, Portland State University, as our population 2. So if these numbers are positive, that means the proportion at Pacific, right, P1, is larger than the proportion at PSU, P2. Right? In fact, it's kind of worth noting, right, that 0 is not in this interval. And why is that important to note? Well, sometimes when we're connecting our confidence intervals with hypothesis tests, we kind of want to know what's the relationship, right? This interval says that even at its lowest, P1, meaning the proportion for Pacific University, is still greater than 0, right? So if everything's positive here, we would say fairly conclusively that it's not possible, or it doesn't appear to be possible, that Pacific and PSU have the same proportion, right? 0 is not in there. So P1 minus P2 can't be 0, meaning P1 and P2 cannot be the same. So P1 is always greater than P2. So this is just kind of looking ahead, thinking, how might I tie this into a hypothesis test? Anyway, that's the basic process. We could find the same interval working through with the test statistic, but this process is a little faster, a little easier.